Hi everyone, in this video I'd like to talk about how to construct a delta epsilon proof of a functional limit. So we will begin with an example that's not as easy as some others, but it's certainly not the most, damn it. Hi everyone, in this video I would like to construct a delta epsilon proof of a functional limit. So we will be proving that the limit as x approaches 2 of x squared equals 4. And if I were to draw a picture of this function, so I'll draw my x and y axis here, and we know that the y equals x squared function looks like a parabola, so I can draw my curve. The idea here is that x approaches 2, so let's say down here on the x-axis, as x gets close to 2, when I then apply function f to my value, I'm getting close to a y value of 4. So in other words, as I get relatively close, let's say within this little zone of x equals 2, and I'm going to call that my delta interval. As soon as I am within delta of this value 2, I am assured that I am close to, relatively close to 4. And how close, you might say? Well, I say within epsilon. So that's what we mean. That's the formal definition of limit to exist, and I will write that down now. So the formal definition says the limit as x goes to a of f of x equals L if and only if for all epsilon greater than 0 there exists a delta greater than 0 such that the absolute value of x minus a less than delta forces f of x minus L to be less than epsilon. Now, that sounds a little bit cryptic, so let's see what is this definition actually saying and how can we use it. So this limit notation, what that means, it means that if for all epsilon, so let's play a game. When I say for all epsilon, what I mean is I'm going to hand you an epsilon. So I hand you an epsilon. This is the game we're going to play. I'm going to hand you an epsilon. Epsilon might be 1, might be 0.5, might be 1/100th. I don't know. I'm going to surprise you, but I'm going to hand you an epsilon. And no matter what epsilon, no matter any epsilon that I come up with and I hand it to you, there exists some delta that you're going to have to find. So let's write a note. You find delta. Okay, so no matter what epsilon I pick and hand you, you can then figure out and find your delta such that these inequalities work. In other words, such that when you pinch x close to delta down here on this x-axis, when you pinch your values down close to delta, this forces your output values, your f of x values, to lie very close to the limit. So close it's hard to even distinguish them. So those f of x, those output values, are lying within epsilon of L. And again, epsilon is something that I get to pick, and I might choose 0.000000001, some really small value of epsilon. And so I'm really restricting and saying I want my f of x values to be, so close to L that you can't even distinguish them from L. So that's the game we're going to play. So you're going to be given an epsilon, and then what you need to come up with is the delta. So let's take a look at this particular example and see how we would construct our proof. So to start our proof, we will start all of these proofs in the exact same way. There's not any room for creativity in the beginning of the proof, but we will get creative later on. So our proofs will start off as follows. Let epsilon greater than 0 be given. Okay, so someone's going to give us this epsilon greater than 0. I'll give it to you, or somebody in the next room is going to hand us an epsilon, and no matter what that epsilon that's given, we're going to have to figure out what the delta needs to be. We need to discover what delta needs to be. So we start off, let epsilon greater than 0 be given. We set delta ... We don't know. We have to figure out what is delta. So I'm going to come over here and I'm going to do some scratch work. And this scratch work is something I always do in private. I never admit to it in public. And I would include it even on a separate paper. I wouldn't show it with my nice proof. I would just go and do it in a dark corner and come back as if I knew what I was talking about all along. But we do need to do the scratch work. We just do it privately. So for our scratch work, here's what we're going to need. What we need is we're going to need f of x minus L to be less than epsilon. And in the context of our particular function, our f of x is this x squared business. The L is the 4. And we need that to be less than epsilon, whatever that is. Now, if I factor this, I have the absolute value of x minus 2 times the absolute value of x plus 2 less than epsilon. And the things that I can control in my proof, I can say, okay, let x minus 2 be less than delta. So this part is less than delta. So that's fine, but what I need is I need for this quantity delta times x plus 2 to be less than epsilon. So let's draw a number line here. This is a number line for x values, and here is the value 2. And I know that I'm going to set x minus 2 less than delta because that's how these proofs work. So that means that x minus 2 is less than delta. That means I'm looking at a little delta interval around 2. In other words, the upper bound of this open interval would be 2 plus delta, and the lower bound of this open interval would be 2 minus delta. So whatever x values I pick, they're going to land somewhere in this little interval. So if I require delta to be less than 1, that tells me something about this x plus 2 quantity. So if delta is less than 1, that means that this upper bound would be at most 3, and this lower bound would be at most 1. So if I'm looking at x plus 2, that's going to be no worse than 5. All right, so what I've got so far, if I come down below, I've got delta times 5 less than epsilon. In other words, I'm going to need delta to be less than epsilon over 5. I also need delta to be less than 1. How to reconcile those two pieces, what I'll do is I'll come back over to my proof and I'll say, okay, here's what I'm going to do. I'm going to set delta to be the minimum or less than the minimum if we're really worried. We can do it either way. Of epsilon over 5 and 1. And again, you could make that a strict inequality if you wanted to, but epsilon is usually quite small, so we are okay with setting it equal. But either way is fine. So there's our delta. We have figured out what delta needs to be. And now we can continue with our proof. We say for x minus a, which in this case is 2, less than delta, observe that f of x minus L, which in this case is x squared minus 4, is equal to the absolute value of x minus 2 times absolute value x plus 2. Well, that's less than, this first piece is less than delta. And it's less than delta because we stipulated that. So we have the less than delta times the absolute value of x plus 2. Now again, using our logic of the number line, we know that the distance between x and 2 is at most delta. So here's the number 2. X lies somewhere in this interval from 2 minus delta, open interval, up to 2 plus delta. And delta is certainly less than 1. So the biggest that this right-hand endpoint could be would be 3, and the smallest that this side could be 1. So x lies somewhere in between 1 and 3. So you could make this assertion that x lies somewhere in this open interval between 1 and 3. In other words, this quantity, absolute value of x plus 2, the worst that's going to be is 5. It's certainly less than 5. So this is less than delta times 5. Using our argument up here, where we said delta is less than the minimum of epsilon over 5 and 1. Well, it's certainly less than epsilon over 5, so we can replace that amount. Replacing our delta here, this is less than epsilon over 5. Again, times 5. Goodbye, goodbye. This shows that the limit exists. Why? Because we said let any epsilon greater than 0 be given. Anybody hands us an epsilon, we can construct our delta as follows. And for pinching our x values close to 2, how close? Within delta of 2. We pinch those input values within delta. Our output values, the f of x minus L, that's going to be close within epsilon of our limit, which was 4.